In this sixth module, we are discussing weak interactions, and in this eighth video, we will talk about the violation of the CP symmetry between particles and antiparticles by weak interactions. After following this video, you will be able to describe the condition for oscillation between particles and antiparticles and their mechanism. And you will be able to explain the violation of the joint symmetry CP in the quark sector. The Kabib-Kobayashi-Maskawa matrix must be unitary, but not necessarily real. This allows a non-trivial complex phase which cannot be removed by a global rotation in flavor space. The existence of such a phase has very important consequences that we will discuss in the following. But first, a reminder. We already saw in video 6.3 that the weak interaction maximally violates parity, P. A good example is the pion plus decay. The dominant decay channel is pi plus going to a mu plus and a neutrino mu. The neutrino produced in the decay must be left-handed because of the structure of the interaction. As the pion is a scalar particle, the mu plus must also be left-handed, which is allowed to the extent that its mass is non-negligible and allows it to have the wrong helicity. The mirror decay, on the contrary, which will produce a mu plus of the correct helicity, is not observed at all, because the W does not interact with right-handed neutrino. This explains why the decay into an electron, pi plus goes to a positron and a left-handed electron neutrino, is so much disfavored, despite its much larger phase space factor. The small mass of the electron requires much more to have the correct helicity and thus suppresses the amplitude of this process. The decay of the charged pion violates at the same time the charge conjugation symmetry C. Under this operation, we obtain a reaction that is forbidden by the fact that the W does not couple at all to left-handed antineutrino, but only to the right-handed antineutrino. Since symmetries C and P are both violated in maximum fashion by charged weak interactions, one might expect that the combined symmetry CP will be respected. This is indeed the case in the example shown so far. For the pion, it is simple to verify that the operation CP converts the pion plus decay into the pion minus decay with a good helicity for the neutrinos, but a bad one for muons only admitted because muons are non-relativistic. These processes are therefore CP eigenstate with the same amplitude. But this is not the case for all the intergeneration weak processes mediated by the W boson. Let's look at the neutral mesons like K0, which contains a D quark and an S bar quark, or B0, which contains a D quark and a B bar quark. This can be converted in their own antiparticle by a second-order process. This reaction is obviously only possible for particles that do not carry any kind of charge. The pseudoscalar meson K0, for example, is an eigenstate of parity but not of charge conjugation, because this operation changes strangeness. K0 contains an anti-quark S bar, so it has strangeness +1. K0 bar contains a quark S, so it has strangeness -1. Therefore, neither K0 nor K0 bar are eigenstates of CP, but one can construct linear combinations K1 and K2 that are eigenstates of CP. If CP is conserved, it should be these two states which decay by weak interactions. If the eigenvalue of Cp were conserved by weak interaction, the eigenstates K1 and K2 will decay by weak forces into final states which contains 2 pions and 3 pions respectively. These final states have the right Cp properties. This is approximately true. The states K1 and K2 are almost identical to the particles K0 short and K0 long found in the list of the particle data group. Because of the two very different space-space factors, one finds that the lifetime of the K short is much shorter than the one of the K long, which explains their name. But the identification K short almost equal to K1 and K long equal to K2 is not perfect. First, the two masses are not quite the same. They differ by some microelectronvolt. The mass difference produces oscillation between particles and antiparticles in time, because both states are not evolving with the same velocity when their energy is the same. Imagine a K1 mesons at t equals 0 at rest in vacuum. Its wave function evolves according to its mass m1 and width gamma 1. The probability density to find the K1 at time t is given by the evolution equation for free particles. The same reasoning is valid for K2, but with mass m2 and width gamma 2. Since strong interaction conserve flavors, including strangeness, a state produced by strong interaction will have a definite strangeness, like K0 or K0 bar. If one produces, for instance, a K0 at t equal to 0, we will have a mixture of equal quantities of K1 and K2 at that time. Now the two components are evolving differently because of the small mass difference delta m. At a later time t, we therefore find a different mixture. If we thus measure the strangeness of the state as a function of time, for example by a strong interaction, we find that it oscillates between K0 and K0 bar with a frequency delta m. So far, the combined symmetry Cp is still respected, but one finds that the long-lived particle K0 long, which is almost equal to K2, has a low probability to decay into pi plus and pi minus, a state which has the wrong Cp eigenvalue. One must thus admit that K0 long also contains a small amplitude of K1. The coefficient epsilon is 2.3 times 10 to the minus 3, which is certainly small, but not 0. Consequently, charged weak interaction violate also the combined symmetry Cp, but only a little bit. This means that the amplitudes of charged weak interaction for matter and antimatter are slightly different, so nature has therefore foreseen an objective way to distinguish them. A complex phase in the Kavibo-Kobayashi-Maskawa matrix allows to introduce this little asymmetry in the mixing of quark states involved in weak interactions, with a phase angle theta, which is about 45 degrees. This describes the phenomenon using the CKM matrix, but does not explain it. Cp violation in weak interaction is a subject of active current research both in the count sector and in the B0 sector. The next video we will discuss neutrino interaction, which are among the most rare processes in particle physics.